All right, students, so what I'm going to do is give you a pretty efficient review of the sections in Unit 3. We're going to do a couple of them here. We'll start with the first one, 3.1. Section 3.1 is about intermolecular forces. This section is not to be confused with intramolecular forces. And so remember that intra essentially were the attractions between or within a molecule. And the intermolecular forces, here these inter are essentially between separate molecules. So that's one of the main difference here. And so in this section, it does help to remember some of the forces or the principles that were affecting some of the forces that we reviewed in Unit 2. But here, a very important thing here is going to be charge is important. Obviously, the distance between the molecules is important. But you really need to make sure that you identify a couple of main forces, and so let's go ahead and identify them, as they will affect how a solid, a liquid, and a gas are essentially going to be interacting with one another, referring specifically to the particles. So the forces that we need to make sure that we reference here are going to be the three main forces. There's a fourth, and we'll identify it. So here, if I kind of spread this out here, let's go ahead and move some of this out of the way, bring it over here to the right. And so here are the forces. And so in no particular order overall, but here the very first force is going to be a what they call the London dispersion force. Now, this force here essentially occurs when you've got a lot of attractions coming in from non-polar molecules. So that's one of the biggest things that we see here with the London dispersion forces. London dispersion forces are often called LDFs because of the acronym LD and the F. So here is the London, the dispersion, and then the force is the letter for F there. Now, the idea here behind London forces is that you need to consider two main things with the London dispersion forces. First off, size will affect the overall force that will be felt. So I'm going to say here that size affects the force that is felt by that in that London dispersion interaction. Remember here that these forces are all obviously occurring between molecules, so they're not actually occurring within the same molecule. And one of the main reasons that the size actually impacts the force is because the size here, remember this is related here to the number of electrons. And so the number of electrons then is going to affect it, because as the number of electrons increases, if there's an increase to these number of electrons, essentially this is going to lead to this one thing called polarizability. I'm going to abbreviate that like that. And polarizability essentially is just going to indicate that those electrons then can be repelled from within the molecule, and that will cause a shift from the area of interaction. So for example, let me just draw you a quick little diagram here. So let's say you've got a molecule like this. So the molecule's right here, same size molecule on this side. These are non-polar molecules, and so they're coming in, and each of them is going to have their own electron cloud. So the electron clouds, if I can represent them briefly here by these green dots, there's an electron cloud surrounding this molecule, same there. And so when they get close, one of these molecules or the other, doesn't really matter, they're going to cause essentially a shift in this electron cloud that we've drawn here. And so instead of being at this region here, what's going to happen is it'll essentially push in a little bit. I'm assuming that the one on the right is pushing in or causing the repulsion, because it's the one that's actually getting closer to it. And so what will happen here is that region now that no longer has any electrons on it, so this region right here, this region here essentially is going to have a slightly different charge, since there are no more electrons in that general region. What's happening here is that it is actually going to have a little bit of a positive nature, because it no longer has a higher density of electrons. On the other side, then, because all the electrons have actually moved to the back part of the molecule, you have a higher concentration of electrons here, so that gives it the slightly negative instance. So here in this particular molecule, you have a dipole interaction. Now this one here, because now you have an electric charge here, if there were another nearby molecule over here or to the top or to the bottom, then that would cause an induced dipole in that one. So eventually you'll start to see that a lot of these interactions are going to be momentary, yes, but they will induce a polar instance in nearby molecules. And that's one of the things about these types of interactions that are very favorable. So let's go ahead and move this section over here to the other side and move it down a little bit. So there's your London dispersion forces. Now, the second type of forces that I want to talk to you about are going to be the dipole-dipole. So let's go ahead and say 2 here, and these are dipole-dipole. And as the name implies, dipole-dipole essentially means that you've got a polar molecule interacting with another polar molecule. Now remember that polar here means that you've got a positive side and a negative side on both of these. So when either of these molecules come into play, when you already have a structure that's already set up, so over here you got a positive and negative, so you got positive over here, negative there. You've got another molecule over here that also has its positive and negative. What's going to wind up happening is that the interaction is going to occur. So notice here we've got a negative part of the molecule here. We've got a positive on the other molecule. So what will end up happening here is that there will be an interaction between these two regions, between the negative of one molecule, the positive of another. Now if you have more molecules, and you're going to start to see a large concentration of molecules, which is what really happens, what you're going to wind up seeing here is that you're going to get an alteration of positive and negative. So what we'll see, let me draw them slightly this way. If I have another molecule coming in from here, if this particular molecule were interacting here with this one on the left, obviously what will happen is if the molecule had a say a negative charge here and a positive charge here, what we see is that there's going to be negative and negative to each other. So this is going to be a repulsive event, which would cause this particular molecule then to essentially turn around and do a 180. So let's see if I can do this here. The shift is going to be essentially here, it's going to rotate. And so what you'll wind up having is going to be that molecule essentially take this shape here, positive and negative. So now you have the interaction between negative and positive. This other molecule then maybe will interact with a nearby one over here. And so that's probably what happens there. And so, but all what's going to happen here at the overall end of this is that you'll wind up having an alternating pattern here of positive, negative, negative, and it repeats itself, very similar to what we had already seen before in Unit 2. It's what's occurring here. Okay. And so that is a condition here that we see with the dipole-dipole. But remember here, the positive and negative is relative to the individual molecules. So it's important that I draw them like this. So these are molecules that have their own positive sides. And so you can have different orientations or different interactions. And so maybe I'll draw this one like this and this one like that. And you can see as long as the interaction is happening between alternating charges, then this is really the effect of the dipole-dipole interaction that's occurring. The other item that I should mention here at this point is what factors influence this particular this interaction here. Well, remember with dipole-dipole interactions, a key component of this is this following, that if the electronegativity of an individual atom, let's say you have an electronegative atom that's causing the negative side of the dipole to occur, as electronegativity goes up, this is essentially going to cause a subsequent effect here that dipole is going to lead to an increase in the dipole interaction or the dipole potential of that particular molecule that will then have an interaction with another molecule. So it's very important that you remember that. The electronegativity will influence that dipole interaction. All right, so let's go ahead and move some of these out of the way. Let's see how we can do this. Let's see if I can move this like this. Put it over here, like so. Come over here, and then I can move this one over here. And then we'll move that one over there. So there's your dipole interactions there on the side. I'll try to make a lot of room so I can address the last couple here on the left-hand side. So the last couple, the first of which I'm going to refer to is the hydrogen bonding. This type of bond is a bond that has some requirements. So the main things that you need to remember here is that this is the kind of bonding that occurs between hydrogen and a electronegative atom. But specifically the atom that we're talking about here are nitrogen, oxygen, and fluorine. Those are the only ones that can be involved in hydrogen bonding. Now, hydrogen cannot be bound to any other atom. That's not going to be allowed. It's not going to work. But that's just essentially a bond that forms between hydrogen and that other atom, typically within a intra, so within the molecule. But remember, these are the interactions that are occurring in separate molecules. So the hydrogen of one molecule will interact with the electronegative atom of the other as long as it is nitrogen, oxygen, and fluorine. So a common example, if you think about it here, you get, you can think of any compound here, but let me give you an example here. Let's say you had NH3, so you had hydrogen this way, and hydrogen that way. It's got its lone pair up top. And let's say that this compound is being interacting here with a water molecule. And so let's say that you've got the water molecule here with a hydrogen this way and that way, lone pair up top. So where is the hydrogen bonding going to occur? Let's say that we draw another water molecule this way. And so let's do that there. So the interactions that could potentially occur here is, notice here you've got a nitrogen. This nitrogen could interact with that hydrogen there. So that could be a hydrogen bonding that occurs. And if you look at hydrogen, hydrogen is bound to the oxygen. So it actually meets one of the requirements. So yeah, that could occur there. And usually the hydrogen bonding, when we draw it, we usually draw it between the atom and the hydrogen atom there. So the electronegative atom, hydrogen bonding with the other one. Another instance of hydrogen bonding would be between the oxygen itself and a hydrogen. So that could occur as well. And so it could occur between any of these three atoms here, just because of the position, the way I drew it here. I mean, you can pick this hydrogen over here in the center or the one on the right. Doesn't really matter. Both of those meet the condition. And I'll just draw that one there. Largely because when you start to look at it, you do need an electronegative atom that's either nitrogen, oxygen, or fluorine. This is oxygen. And the hydrogen must be bound to one of those three, and here is nitrogen. So that hydrogen, as well as this hydrogen here, or this one, would definitely qualify as a pairing for the hydrogen bonding scenario. So both of those are valid there. Now with respect to the last type of bonding, let's go ahead and make some room here. Let's just move this up a little bit here. The last interaction that I want to refer to here is a little bit of an offshoot of number 2, and that is that we're going to be talking about a ion dipole. And the only thing here that's a little bit different is, on the one hand, you do have a polar molecule. With the dipole, you're going to have yourself a positive and a negative side. And with regards to the ion part, remember here that the ion can either be positive itself or it could be negative, in which case, since the dipole molecule has a positive and negative, you wind up getting a similar type of interaction as you would within the dipole-dipole, where here the positive side of the polar molecule will be attracted to the negative ion. And so what you'll find here is that you're going to get this negative ion where you have it's going to be surrounded. And so without going too detailed here, we're just going to take the negative ion here, and you're going to wind up getting a molecule in which the positive side of the molecule will essentially surround the negative, and then on the flip side, if you've had the positive then would be surrounded by the positive side of things. I'll just change color here just for, surrounded by the negative, I'm sorry, but I'm just going to change color here so that we can kind of distinguish the two. Okay, and the examples that I shared here before was what happens when you dissolve NaCl in water. And so to give you that example as well, the NaCl will generate here Na plus ions and Cl minus ions. And so just, I'm going to do the sodium. So if you have the sodium ion, which is positive in water, we'll essentially have the water molecule having the oxygen atoms facing the sodium ion, and then you'll have a variety of these, or several copies of them, surrounding the sodium, and that would allow you then to have that sodium ion isolated. This is one of the processes that occurs when you dissolve various solids by water, especially if that solid tends to be a ionic solid. So those are the four different types of interactions that you need to be aware of in the 3.1 section. So make sure that you go through and look at that. But before I leave you, the next question that you need to wonder here is what happens? Why is this important for us? Well, the reason we need to explore all of this is because we need to look at the properties that are affected by all of this. And so I'll create a separate subsection for this first 3.1 video. We'll call that one 3.1b. But I'll explain a little bit more how the properties are affected. But for right now, these are the four types of interactions.